Welcome to the first video in Chapter 7 on the probability of several variables, where we'll start Section 7.1, where we're going to review random variables and their distributions. The goal of this section is to review concepts of probability and random variables in order to build on them in subsequent sections. The assumption here is that you have seen these concepts in a previous course. We will not do any examples either. We'll just touch on the definitions quickly and propositions quickly to refresh your memory. Definition 7.1.1. We will call x a random variable if its values depend on chance. And please notice that this is a capital X. When we use capital letters, we are going to be referring to random variables, variables whose values are unknown but depend on chance. We are going to call the set of values. So the set of all possible values that a random variable may take, we're going to call that its support. A discrete random variable is one whose support is finite or can be listed in an infinite sequence. A continuous random variable is one whose support is an interval. And it's important to note here that the definitions of random variable and support above are informal, but they're good enough to suit our purposes. Definition 7.1.2. If x is a discrete random variable, then the probability mass function, or PMF for x, is a function p sub x of x. Please note the distinction. Capital X is the random variable, little x is a value that big X may take. That this PMF is the probability that big X takes the value little x. If y is a continuous random variable, then the probability density, not mass, but density function, or PDF, for y is a function f sub y of y, such that the probability that a, some value a, is less than or equal to y is less than or equal to b, meaning that random variable big Y takes values between a and b inclusive, is the integral from a to b of f sub capital Y of little y dy. Remark: when there is more than one variable in a given context, as in above where we have x and y, we will write the PMF or the PDF for the variable with a subscript to make it clear which variable is being referred to. Definition 7.1.3. The cumulative distribution function, or CDF, for a random variable x is f sub x is the probability that x is less than or equal to, or x takes values less than or equal to little x. That is the same regardless if x is discrete or continuous. So that is the same definition. How we calculate them is different, of course. So if we're talking about a discrete random variable, then the cumulative distribution function is the sum over all values j such that j is less than or equal to a little x of the probability mass function. So that's little p sub x of x, where this p sub x of x, that is the PMF, or the probability mass function. Now if x is continuous, right, we still have the same definition. It's the probability that x takes values less than or equal to this little value x. But for a continuous function, we have to integrate from minus infinity to x of f sub x of t dt, where f sub x of little x, this is the density function for x. Notice the difference. X is up here, right? That's little value of x. This is big X, the random variable x. My dt is a dummy variable, so I could have written dt, I could have written anything in here for the PDF. In the continuous case, f sub x of x, the cumulative distribution function, if we look at this reminds us of the fundamental theorem of calculus. and indeed the cumulative distribution function is an antiderivative of the density function in the case where x is continuous. In particular, this means that if we take the derivative of the CDF, we get the PDF. Proposition 7.1.1. If x is a random variable with cumulative distribution function f sub x of x, then the probability that a is less than x is less than or equal to b, which again means that the probability that this random variable, capital X, takes values between a excluded and b included is calculated or calculatable with the cumulative distribution function, f sub x of b minus f sub x of a. And that is true whether x is discrete or continuous. Doesn't matter. If x is discrete, then writing less than versus less than or equal, that's important. It makes a big difference. However, if x is continuous, one can play a little more fast and loose with these inequalities. One can write less than or equal to interchangeably, because for a continuous random variable, the probability of getting a single value, right, the probability of being exactly at A or exactly at B is 0, and so it doesn't matter whether we include or exclude the endpoints in the case when we're talking about a continuous random variable. In the next video, we're going to go a little bit further and look at expectation, expected value, and an important theorem based on expected values and integrals.